In this video, we're going to look at a special case of factoring called the sum and difference of cubes. But before we look at factoring, we are going to expand this product first. So I'm going to use an area model. So on the sides, I'm going to have x plus 2. On the other side, I'm going to have x squared minus 2x plus 4. So from here, I'll multiply the sides into our area model here. So I will have x times x to give us x cubed, x times negative 2x to give us negative 2x squared, x times 4 to give us 4x. Then with the second row, 2 times x is 2x squared, 2 times negative 2x is negative 4x, and 2 times 4 will give us 8. Now, when we go to write this out, combine like terms, hopefully you see that we're going to have some terms that cancel. Here we have a negative 2x squared and a positive 2x squared, which will cancel to 0. Here we have a negative 4x and a 4x, which will also cancel to 0. And so all that we're left with when we multiply this binomial and trinomial is x cubed plus 8. So now that we know why this product goes down into just a binomial right here, this will help us go backwards. So you'll notice that in the beginning we saw lots of 2's. So we have a 2 here, a 2 here, and then 4 is 2 squared. Well, it's not a coincidence. That's because this 8 right here, if you take the cube root of 8, we would end up getting 2. Cube root of x ends up giving us the x. And so just kind of understanding that when we multiply these together, that these middle terms cancel, this is what we're left with. That's going to help us recognize this pattern and go backwards into factored form. So one thing that we want to know is that the sum and difference of cubes works when we have a binomial. And that binomial has to be 2 perfect cubes in order for us to factor it. So this will work for both the sum and the difference of cubes. So with this first one, we have a sum of cubes. And so we will start it by taking the cube root of both of these terms. So that will give us an x plus 5. Now, when we multiply this out, we know whatever we put here will need to multiply to the x to give us x cubed. And so that tells me that I need an x squared. Whatever term I end up putting on the end needs to multiply to the 5 to get 125, which is 25, which happens to be 5 squared. So from here, what goes in the middle? Well, if I multiply 5 times x, that's going to give me 25x. But I need it to cancel. And so whatever I place right here in the middle is going to multiply by that 5. Well, I want it to cancel with 25x's, so I'm going to make it a negative 5x. And so we basically just followed this generic form. Now, if we were to use the area model like we did over here, we would expect some terms to cancel and go back to x cubed plus 125. Same idea here. This time we're just subtracting, so it'll change our signs a little bit. How we start it, cube root of x is x. Cube root of 27 is 3. And we make it a negative since it's a difference now. When we go to multiply, I know I need to multiply x squared by x to get x cubed. I know that I'm going to multiply the negative 3 by a negative 9 to get, or a positive 9 to get negative 27. And then right in here, if I were to multiply 9 times x, that'd give me 9x. And so I need to cancel these 9x's out. And so I'm going to multiply that negative 3 by a positive 3x to get those to cancel. That would give us a negative 9x. So that would help those middle terms cancel. Okay, so with our examples, our first example, we have an 8 in front, which makes it look different than the ones above. However, it's still okay because 8 is a perfect cube. So now instead of x plus 3, we will have 2x plus 3. From here, 2x times 4x squared would give us the 8x cubed. This 3 would be multiplied by a 9 to get 27. And then now, same idea, this 2x and this 9 will give us 18x, but I need them to cancel. So whatever I place here and multiply by 3 needs to give me negative 18x. So I would have to have negative 6x. Notice that 6x comes from 2x times 3, and it needs to be negative since this one was positive. Okay, so example number 2. Keep in mind that one method of factoring that's always helpful is greatest common factor. And so right away, I'm going to pull out an x. I'm then left with 8x cubed plus 1. This is the sum of cubes. That x stays out front. Cube root of 8 is 2. Cube root of x cubed is x. Cube root of 1 is 1. From here, we use 2x squared. So that'd give us 4x squared. 1 squared is 1. 2x times 1 is 2x. That stays positive. That needs to be negative to make terms cancel. Example number 3, that original problem was wrong, so hopefully you've adjusted yours to be 686 x cubed minus 2. Now looking at this right away, 2 is not a perfect cubed and neither is 686. However, thinking about that greatest common factor, if you start by pulling out a 2, you're left with 343x cubed minus 1. That 2 needs to stay there. Now we have a difference of cubes. The cube root of 343 ends up being 7. And then we have our x. Cube root of 1 is 1. Subtraction. Follow the same pattern. 7x squared is 49x squared. 1 squared is 1. 7 times 1 would give us 7x, positive and positive. All right, moving over to example 4. This negative kind of in the way. If you don't like it, you could pull a negative 1 out. That will change your signs. It'd be a 27x cubed minus 125. That negative has to stay there, but now we could factor what's remaining. This would give us a 3x and a 5. From here, 3x squared is 9x squared. 5 squared is 25. 3x times 5 would give us a 15x. Same idea in example number 5. I would definitely pull out a negative first. Makes this easier to look at. X cubed plus 8 is what we're left with. Same exact pattern. We have an x plus 2. X squared minus 2x plus 4. Example 6, your greatest common factor. There's a little bit more to pull out here. Notice that both have an x in common. You could also pull out a 2. You could actually pull out, yep, I think a 2 is the largest that you could. So we can pull out a 2x. That will leave us with 125x cubed plus 64. Now we're left with the sum of cubes. So we'll have a 5x and a 4. That would leave us with 25x squared minus 20x plus 16. And we're done.